Hello and welcome back. Before we get started taking notes, let's go back to our previous problem on our previous worksheet. Number 7 on the back page of the previous worksheet, you were asked to graph two equations and, for a sort of challenge, find the intersection of those two lines that you graphed. So let's graph the first one. Y is equal to 2x minus 4. I got onto negative 4, which is the y-intercept. And my rise over my run is 2 over 1. So I'm going to go up to 1, 2 over 1. To make sure I'm going to get a straight line, I'm going to go ahead and do it twice. Up 2 over 1. And I'm going to draw that line. We go to our second line. Y is equal to negative 1/3 x plus 3. Our y-intercept is positive 3. Our rise over our run is negative 1 over positive 3. So I'm going to go down 1 to the right. 1, 2, 3. And draw my line. It looks like they're intersecting at the point 3, 2. But to make sure, I'm going to go back to my first line, and I'm going to use my rise over run from the previous point one more time. The rise is 1, 2. The run is 1. So you notice that the two lines do indeed intersect at the point 3, 2. So the intersection is 3, 2. The reason I wanted to go back to this problem on the previous worksheet is that this intersection is the focus of today's lesson. Our lesson is going to focus on finding intersections of two lines. So if you take out your notes, go ahead and label today's notes. You don't need to label this previous part, but brand new on your notes, label them solving linear systems by graphing and by matrices. Our first term is a solution to a linear system, and we're going to define a solution to a linear system on a graph and on a table. On a graph, the solution is what we just got through finding. It's the intersection of two lines. So a solution to a linear system is an intersection of two lines. Notice that intersections always occur at a point, so our point is going to be x, y. What we're going to do next is we're going to go ahead and use our graphing calculator to see if we can't find the same intersection, 3, 2. Now my program only allows me to either use the mouse or the writing utensil, so all the writing is going to disappear for a moment while we go back and look at our calculator. Take out your calculator, and you want to go ahead and clear the RAM if you have not always. That's a great place to start every time to make sure you start with a fresh calculator. So we're going to go second plus, that brings up our memory screen. 7 means we're going to reset. 1 says all RAM, and 2 tells me I'm going to reset all of my RAM. When you do so, you should see a message telling you that your RAM is cleared. If you have TI-83 and not a TI-83 Plus, you'll see a message that says done, meaning that your RAM is clear. So we've cleared our RAM, and what we're going to want to do is we're going to want to graph, or have the calculator graph for us, the two equations that we just got through looking at. So to put the equations in the calculator, we go to the y equals screen. So you go to y equals. Notice all these buttons along the top end right here, all these have to do with graphing. So anytime you want to do anything with graphing, it's usually going to show up at these buttons right here towards the top of the calculator. Y equals. Well, y is equal to 2x minus 4. So I'm going to go to my calculator and I type 2. X is the letter button next to alpha. It says x, t, theta, n. So we type x. Now here's the important part. It's minus 4. Anytime you're subtracting two numbers from each other, you use the minus button. But if we go on to our next equation, press enter, it's a negative 1/3 x plus 3. So since it's a negative 1/3, we're going to use the negative button. Negative 1 divided by 3 x plus 3. So now we have in our calculator the two equations in slope-intercept form that we were given on the previous problem. Let's go ahead and graph them. So if you look at the top row of buttons, you'll see the word graph. So we're going to graph it. And you should see a graph that looks very similar to the graph that we made on our own graph earlier by hand. What we want to do is we want to have the calculator find the intersection point for us. To do that, you can type in second trace. If you look above trace, you'll see written in yellow letters the words calc. That means calculate. So we're going to calculate, and we want to calculate the intersection. So you go enter for intersection. A message pops up in your calculator, says first curve. So that's the calculator asking you, what's the first line that you want? Blink, blink, blink. Is this the first line? You say, well, yeah, sure, that's the line I want. So you press enter. Notice that the blinking cursor moves to the other line. It says second curve at the bottom of the screen. That's your calculator's way of asking you, is this the second line you want? So you press enter, telling it, yes, it is the second line that I want. Then you get a message on your calculator that says guess. And that's the calculator's way of playing a game with you. It says, can you guess what the intersection is? You don't have to play the calculator's game. You can just press enter, and you'll find out the intersection is 3, 2. Please keep in mind the intersection must be written as an ordered pair. So when you wrote the solution to this system, you would write 3, 2 in parentheses. The second thing I want you to do is go to your table. So if you look at above graph, you'll see the word table written. So you write second graph. That's how you get to your table. And I'd like you to look for a moment and see if you can identify where the solution is on the table and how you can tell from a table when you have found a solution. So if all you were given was a table, could you tell me what the solution looks like? Hopefully by looking at it, you'll notice that when x is 3, both y values are 2. So on a table, you know the solution is where the y values repeat. And let's write that a different way. Let's say when y1 equals y2. So you notice y1 and y2 are the same for the same x. So both of them are equal to 2 when x is equal to 3. It's going to be important to notice this because that's going to help us answer the next two challenging questions that I'm going to have for you. So please remember that a solution to a linear system is where two lines intersect. If you're looking at a graph or on a table, it's where the two y values are equal to each other. I'd like you to take a moment and see if you can't solve these next two systems using your graphing calculator and or by table. As a hint, these two systems are going to give you something really weird when you try to find the solution. So it's going to be something totally different. If you're watching this at home or this is the first time you've seen it, I encourage you to try to solve these systems on your own. See if you can't find out what's going on with the two systems, and we'll come back together, pause the video, we'll come back together and we'll talk about hopefully what you found. Also, to get you started, notice that in all four equations, by the way, these are two separate systems, so you're going to solve these separately, but in all four equations, they are not in the form y equals mx plus b. So the very first place you want to start is to get them into y equals mx plus b form so that you can either put them in your graphing calculator and go to your graph or go to your table. You can also try to graph them by hand if you would like. Go ahead and take a moment to do that. Pause the video, and when we come back you can check to make sure you got them in y equals mx plus b form first correctly, and second of all, we'll summarize hopefully some of the things that you found that were different about these two systems than the previous system of equations that we saw earlier, meaning the two equations that we graphed earlier and found the intersection to be 3, 2. Go ahead and take a moment to do that. Alright, let's look at our first system. First system wasn't in y equals mx plus b form, so I had to subtract the 2x, and that left me with 5y is equal to negative 2x plus 6. Didn't need it to be 5y, so I divided every term by 5, and I got y is equal to negative 2/5 x plus 6/5. Let's look at our second equation. 4x plus 10y is equal to 12. Kind of the same sort of steps. You subtract 4x, and you get 10y is equal to negative 4x plus 12. Divide everything by 10, and you get y is equal to negative 4/10 x plus 12 over 10. We probably want to reduce, and by the way, you do want to go ahead and reduce all of your fractions if possible. That'll give us negative 2/5 x plus 12 over 10 gives me 6/5. At this point, when you got ready to put these in your graphing calculator, you might have noticed that the two equations you got are exactly the same. Y is equal to negative 2/5 x plus 6/5. Don't worry, you haven't done anything wrong. Sometimes this happens. Sometimes we have two systems that when we get in y equals mx plus b form, it ends up being the exact same equation. Well, okay, still doesn't change what we were asked to do. We're asked to solve, so we're either trying to find the intersection or where the y values are the same. So let's go back to our y equals screen. Hopefully you've cleared your RAM, and I have not, so I'm going to go ahead and just clear right here. And we had negative 2/5 x plus 6/5. And I'm going to go ahead and put it in twice. So negative 2/5 x plus 6/5. When you graphed, okay, so we graphed the first equation. Now let's wait for it to graph the second one. Oh wait, it's the exact same equation. So when you graph the exact same equation twice, yeah, I know, you end up with the exact same line. Well, let's go to the table. Kind of hard to find an intersection here because it's the exact same line. How do you find out when the same line intersects itself? You might have already caught on, but let's go ahead and go to the table anyways and see what's going on. Remember, our definition of the solution of a system on a table meant that the y1 is equal to y2. Well, okay, so that means my solution is 0, 1.2. Oh, but wait a minute. The y values are also the same at 1 and at 2 and at 3. Well, okay, the y values are the same everywhere. You know, you can scroll down as far as you want, and in math we say that, well, that's infinitely far. So when I ask you to solve the system, you have to somehow tell me what this means. Like, I say solve, that means find the solution. You can't tell me what the solution is because, well, every x value is a solution. So when you run into a situation like this, you want to tell me that are infinite solutions. And how did you know there were infinite solutions? Well, let's look what it is. On a graph, it's the same line. On a table, same y values. And the equation, I'm going to abbreviate it EQ, the same equation. Go to our second example, you'll get y is equal to 3/2 x minus 5, and your second equation you should get y is equal to 3/2 x minus 1. when you put these two equations in the calculator, and maybe before you even put them in the calculator, you notice that, well, the slopes are the same, but the y-intercepts are different. So let's go ahead and put these in our calculator. 3/2 x minus 5 and 3/2 x minus 1. So it was 3/2 x minus 5 and oops, 3/2, not 3/5. 3/2 x minus 1. And we're going to graph it. So there's our first line, and there's our second line. So 3/2 x minus 1 and 3/2 x minus 5. Well, when you graph these two, you should notice that the two lines are parallel, and I'm asking you to find the intersection. Well, the intersection of parallel lines, well, wait a minute. Parallel lines never intersect. So guess what? There's no solution. If you went to the table, you'd find out the y values were never the same. So anytime you run into a situation like this, where the two lines are parallel, you say no solution. So on a graph, it was parallel lines. From the table, the y values were never the same. And from the equation, remember the only time two lines are parallel is when the slopes are the same. Alright, we're going to go ahead and summarize what we just got through going over on the previous examples in the next 3 questions off your worksheet. First question, if a system of equations has one solution, what does this solution look like on a graph? Well, one solution is where the two lines intersect. So you can say something like where the two lines cross, or it's a point where the lines intersect, something along those lines. I'm going to write a point x comma y where the lines intersect. By the way, if you have not taken the time to fill this out on your own, please go ahead and pause the video and see if you can't fill it out by yourself. You may not end up with the exact same thing that I have, but that's okay, so long as you have the same idea. All I'm getting for the first one is, well, what does it look like on a graph? Well, it's where the lines cross, or where they intersect. What does it look like on a table? We just got through saying that. A solution is where y1 equals y2. And if there's only one solution, this should only happen once. How can you tell when a system of equations has only one solution? And what I'm asking here is, how can you tell it only has one solution from the equation? Look at the slope and the y-axis intercept. Let's hold off on B, and we're going to answer number 2 and 3 first, and then come back to B. Number 2, what does a system with infinite solutions look like on a graph? Well, if you remember, it's the means, if you graph two equations that have infinite solutions, that means all you've really done is graph the exact same line. What does it look like on a table? Well, y1 is equal to y2 everywhere. How can you tell from the equation? Remember, the equations are the same. Meaning m1 is equal to m2, the slopes, and b1 is equal to b2, the y-intercepts. Alright, what does this system with no solutions look like on a graph? Well, they have parallel lines. Next question's a little bit different. If you do not see the same y values for y1 and y2 on your table, does this always mean there's no solution? It's really a tricky question, and this is a word of caution and a word of warning when trying to use your table. Sometimes your solutions will be decimals, and if your table is set to show you only whole numbers, it's not always going to show you when you have no solution, because your table is only going to count by 1, 2, 3, 4, 5, 6, 7, so on. So it's going to skip 1.1, 1.2, 1.3. So the answer to this question is no. Just because they're not the same does not mean there's no solution. Not always. And you can graph these two equations and then go to your table to verify that. So I encourage you to put both these equations in your graphing calculator. Do second trace the intersection, find the intersection, write down that ordered pair, and then go to your table and see if your table shows you that exact same ordered pair. Let's go to 3b. How can you tell when a system of equations has no solutions? So looking at the two systems, you'll notice that parallel lines always have the same slope. So m1 is equal to m2. Uh-oh. Yeah, we just had something kind of weird happen here. Over here you told me that two equations are the same. That means you have infinite solutions. So m1's equal to m2. But how do the two equations have infinite solutions and no solutions? Well, the trick was, if you go back and look at the previous two examples, even though the slopes were the same, the y-intercepts weren't. Alright, now that we have this information, it'll help us find out how can you tell when you only have one solution. Well, we know if the slopes are the same, you're either going to have infinite or no solutions. Which means if the slopes aren't the same, you're going to have one solution. So how can you tell from equations that you have one solution? Real easy, the slopes aren't the same. And if you think about two lines that have different slopes, no matter what those two slopes are, if the slopes of the lines are different, they will eventually intersect somewhere. Alright, this pretty much wraps up the conversation of how to solve using graphing or using a table. We still have one more major objective to cover, and that is how to solve a system using a matrix.